All right, good morning, everybody. This is Jorge Fernandez with KETIV here once again for KETIV AVA. Today's session is Inventor Dynamic Simulation, and I'm very happy to announce that today we have guest speaker Jay Tedeschi from Autodesk. I've known Jay for a long time, very well respected, very knowledgeable in a lot of the Autodesk products, of course. So I look forward to having him on more of our presentations. And I'd also like to comment really quickly that Inventor Dynamic Simulation was another suggested topic from the community too. So keep those coming. Keep any recommendations of topics you'd like to see. By all means, keep letting us know. The next upcoming sessions will have process automation with Autodesk Vault, more about Fusion 360 workflow, and then another session on Inventor where we go into constraints and joints. So look forward to having all of you there. Don't forget that also these sessions are recorded and can be found on our KETIV playlist for AVA. So with that, I'd like to go ahead and turn it over to Jay, who's going to talk to us more about dynamic simulation in Inventor.
Thanks, Jorge. Well, good morning, good afternoon, good evening, depending on what geographic region you are listening to this from. As Jorge pointed out, my name is Jay Tedeschi. Senior Technical Marketing Specialist. I've been at Autodesk for, I think it's 22 years. I'm in my 22nd year, I think. I can't remember. It's been a long time. In any case, the topic we're going to discuss today, we're going to be looking at dynamic simulation and how to use dynamic simulation in the larger work frame of what you're trying to do or what information you're trying to glean from mechanical assembly. Now, the assembly we're looking at here, this is a machine that's built by one of our customers. This is a sub-assembly. The entire machine, the customer's name is Osgood. You've probably seen this data set represented quite prominently up on our web page. It is one of the largest data sets to date that Inventor customer has created. There's almost 24,000 components in the fill-up assembly. It is a yogurt filling machine, so that this machine in particular does the task of essentially ordering or collating yogurt cups and then filling them with product, the fruit and the yogurt itself. The machine we're looking at right here on the screen is used to test the integrity of the foil cap. So once the cup has been filled, there is a adhesive backed, it's got adhesive around the edge, and essentially it is layered down on top of the yogurt filled cup, and that seals the cup. Now keep in mind that this machine functions, it tries to cycle these through 2 cups per second. That is the cycle rate of the entire assembly. And to test for the integrity of how well that foil cap has been sealed, this machine is used. And essentially what happens is, as you can see down here, these gray metallic pieces are basically cycled down and they touch the top of the foil. And these have a thermocouple which is inserted into the side. You can see it right here. It's just a placeholder for the thermocouple itself. So what it does is it actually superheats the air that is underneath the foil cap, and the foil cap stretches as the heated air expands, and that is how they detect whether or not the foil cap or the foil lid is in place. So what we're going to do is, over the next 15 minutes or so, we're going to analyze the motion and the stresses that are generated by that motion on that assembly. So with that, let's get this rolling. So I'll start by activating a design view called Dynamic Simulation. Now this is if you look over here into the browser, you can see I have level of detail representations and view representations for Dynamic Sim. The view rep does nothing but just essentially isolate a specific location on the screen and visually turn on and off components that I do or do not want to have visible on the screen. The level of detail rep, on the other hand, that's the key. This is something that I've been doing since dynamic simulation was first put into the Inventor product, and that is limit the number of components that you're working with when you do a dynamic simulation run to those components which are playing an active role in the simulation itself. Now, I'll state that again. Use level of detail representations to limit the number of components which are active in the dynamic simulation run to those components which play a role. Now, for example, a large section of the static frame is not basically going to be doing anything in this simulation. It doesn't move whatsoever. However, if it's enabled, if you have a level of detail turned on that includes everything, every single component in the assembly is going to be essentially assessed to determine whether or not it is moving or not. So it's in your own best interest to limit what you're working with on screen to those components that you're actually looking for results from. So once we have the design view activated, I'm going to activate a level of detail rep named Dynamic Simulation. And what that does is it essentially, as I pointed out, just limits what I'm looking at or what I'm working with to what's actually on the screen. From there, we go to environments, and from environments, we go down to Dynamic Simulation. Now, let's take a look at the simulation player here. So, as you can see here in the dialog box for Simulation Player, by default, every simulation has a duration of 1 second. Excuse me. I just cut that down to half a second. As I told you guys, this thing cycles 2 cycles every 1 second. So I'm just trying to look at 1 cycle of operation. I'll get more on that in a second. So I'm going to set the duration of the simulation itself to half a second, and then let's go ahead and take a look at the screen next to it, which is the number of iterations, the number of segments or time slices that we're going to squeeze into that half second. So, for example, if I set that to 10, then every tenth of a second with a half second. I'm sorry. If I set that to 5 for iterations, we would every tenth of a second have 1 iteration of movement. Now, the problem with that is, and this is something you have to keep in mind, how coarse or fine are the results that you're looking for. So, for example, if I set that, let's say we set it to 10 and we had 1 iteration every fifth of a second. If there was a motion or a force which was generated at a quarter, at 1/4 or 1/2 of that fifth of a second, then I would totally miss it. I wouldn't be able to get any results from that whatsoever. So you always need to keep in mind when you're setting up your simulation what your, I hate to use the term level of detail, but that's exactly what we're talking about here, and that is how fine or how coarse an event is this, okay? So that being said, we're going to set that to 50. So we're going to get 50 time steps or 50 iterations generated at that half second. Now, once that's done, let's go ahead and look at the browser here. And over here in the browser, you'll see that based on the assembly constraints which exist in the assembly, dynamic simulation automatically goes about creating either grounded or mobile groups. Okay? Mobile groups are components which, basically by virtue of the assembly constraints which are applied to those components, allow them to move in some direction. So those will show up in the browser as welded groups. Everything that's grounded and can't move whatsoever will show up as grounded. Now, one of the first things we have to do is make sure that our reference frame is unified. So if you look here, this prismatic joint that I'm looking at in the browser right now, that prismatic joint is the one that we're going to use to drive the motion of the entire assembly. But if you look, does everyone see the yellow and green axes? Those represent the reference frame for each of the individual components that are selected as the basis for that assembly constraint. So you know when you assign an assembly constraint, you pick entity 1, you pick entity 2. Well, by virtue of where the origins are for the components which are selected, and I'm not talking about the global origin, I mean where you select the component to apply the constraint, where it assigns origin, as you can see, those two origins are different, and they need to be a single unified reference frame for our results to be valid. So what we're going to do now is go ahead and go through and edit that prismatic joint. So we'll flip the z-axis, and now let's set the origin up here to the center of that hole on the plate. So for both of these components, we're setting them to the exact same location. So now our reference frame is aligned, as you can see, so we are good to go, at least as far as that is concerned. Next up, we're going to format the part that we're actually going to do the analysis on. So we have to select it and flag it as being exported to FEA. Now what happens next is the dynamic simulation looks at that component and then determines where there are joints for dynamic simulation, and the forces that are generated at those joints have to be applied to a face. So essentially, dynamic simulation works like a big free body diagram tool. And in that regard, it is generating the forces at the joints themselves. Those forces then have to be applied to model faces, and that's what we're doing right here. We're basically telling dynamic simulation, when we generate the forces from the dynamic simulation run and prep it for going to stress analysis, those will be the faces that you apply those forces to. Next up, we're going to insert a joint, and this is going to be a 3D contact joint, and that is because this hinge here actually rotates on that pin, and we just want to see accurate behavior when we run the simulation. We want to see that pin, we want to see what kind of basically behavior is created as it rolls through the range of motion. Next up is we essentially are going to use the input grapher to graph the movement of the tool, of the entire assembly. So we'll pick our duration. So I'm going to insert a point here. The actual motion is 24 millimeters. Let me pause this right here. So what we've done, as you guys can see, remember I said the duration of my event is half a second. So there's our half second. So what we did was we double-clicked here in the center to add a point at 0.25. So you can see our starting point is at 0 seconds. Our ending point for this segment right here is going to be at 1/4 of a second, 0.25 seconds. The range of motion during that period from 0 to 0.25 seconds is going to be 24 millimeters. So we go ahead and enter that in. Okay? Now what I just did there was we determined the type of motion. So as you see, by default, we end up with a linear ramp. And a linear ramp would be a very abrupt movement, and that's not what happens. The way the machine works, it starts slowly accelerating, it accelerates up to its maximum velocity, and then just before it changes direction and starts pulling up again, it starts to slow down. And that's why we use a cubic ramp here to approximate more closely the actual movement of this assembly through a single cycle. Now we'll do that again. Watch, I'm going to select this segment right here. So let's click. It highlights in yellow. Let's set that to 0, so that'll zero that movement back out again. And then we set it to cubic ramp so that our movement is smooth, and we insert that as the natural or native behavior for that segment of movement. Now there's another thing we have to do, and that is define the motion which is outside of the event we've defined. We've defined an event which goes from 0 to 0.5 seconds. So what we're telling it now is that this is not an isolated movement. This is part of a cyclical movement. So what we're going to determine or define here is that to the left or right of either one of these points at 0 and 0.5, we want it to start moving again. Even though it's not going to do it, we're basically telling the dynamic sim tool that it's not coming to a halt here, that it basically repeats cyclically this motion. And that's how you basically do it. So we say cyclical, the start point is at 0 or 0.1, and that's it. So we have now defined, and you'll notice that in the input grapher here, we get a nice little approximation of the acceleration curve or the motion curve that we have defined for the dynamic sim tool. At this point, there's nothing left to do except run the simulation. So we'll hit the play button, and it takes a second. And as you can see, so the little handle there came down and hit the top of the thermocouple and then stopped moving. And that's it. That's 100% of the range of motion we defined. So it's taking a second to process, and now what we'll do is go ahead and take a look at the motion that was generated through the output grapher. Now, the first thing we'll do in output grapher, just to essentially show you, well, for no better reason other than I added it, and now we can look at it. I added it in there, the 3D contact constraint, so that I could show you some of the additional capabilities. So as you can see, I go to the force joints over here in the output grapher, and we look at the 3D contact. That's the joint that we added between the handle, the pin handle. What we're doing here is we're looking at the contact joint that we added, and we're looking at the category of penetration. Now, obviously, we're not getting any penetration here because this is these are solids, but what this penetration field actually allows us to look at is how the movement, as this thing comes down and bounces off the top of the thermocouple, you can see that at 0.1 seconds, it's moving at about 90 thousandths of an inch. And then that movement settles down to where it's almost not moving at all. It's moving, it looks to be, a couple thousandths of an inch, if that, as we get further through the event. So by the time we get out to half a second, it's almost stopped moving entirely. So that's just how you analyze the movement of these joints, or the values of these joints. You can always right-click on the values itself. I can say find the maximum values, and also anywhere that I click in the output grapher will automatically advance the model, the assembly of the model, to that point in time when I select in the output grapher itself. Now for this, let's take a look at the position. So we're looking at, this is the prismatic joint that we modified to define the motion, and as you can see, this is the exact motion that we defined. This should be the exact same curve. If you look over here in the output grapher, its position, that is the exact same curve that we input through the input grapher when we input the motion, we force that motion in there. We can search the maximum. I right-click on that field, search maximum. It finds exactly that, and you'll notice that, again, as I select in the output grapher, the model is automatically advanced to that point in time. So now we're layering the force that is generated at the prismatic joint, as well as the position, and we search for the maximum, and these are the joint properties themselves, or these are the properties which are generated at that time step. So we're looking at a maximum of 580 newtons of force, which is generated on that little pin. The average over this time step is 483 newtons. Our standard deviation, the amplitude, as well as information about the time step itself. Now, what we're going to do by selecting over there is we've now flagged that time step as being exported for finite element analysis. So that's the maximum force which is being generated, and we're exporting that to the part. Now, any of you who have ever done stress analysis with Inventor have probably seen when you set up a simulation, you always have the opportunity to, if you've never used Dynamic Sim, you've probably never done it, but you can basically utilize motion loads from Dynamic Sim, and that's exactly what we're going to do. I'm going to start by creating or activating a level of detail rep called Isolate, which just isolates the assembly we're going to work on. We're going to create a simulation. We're going to use motion loads analysis. These are the motion loads we just generated. There's only one. Now, up in here where it says time step, if I had selected, and you can do this, you know how in the stress analysis tool you have the option of creating multiple load cases. We're going to have a single load case here because we only output a single time step. But I could have output as many time steps as I wanted to from Dynamic Sim if there were multiple events where this part was being subjected to stresses. We will also change our contacts from default to bonded. All of these parts are bolted together, so the default contact type for that type of environment would be sliding with no separation. So if, for example, I know it's hard to think about, but if these components were subjected to shear forces, they would slide ever so slightly. It's not like they're welded together. So that's how you should think of these contacts. So a bolted assembly such as this, the main contact type should be set by default, in my opinion, to sliding with no separation. So here come all the motion loads from Dynamic Sim. We can turn the display of those on or off. And the beauty of using Dynamic Sim for this is that it takes all the guesswork out of it. Essentially, all I have to do at this point is define the constraints and double check and make sure that the material itself is set up the way we want it set up. We could also set an alternate material if we wanted to do some kind of what if. So I'll add a frictionless constraint here between the bottom of that and the top of the thermocouple. And we'll add pin constraints where it essentially bolts to the thermocouple itself. So these are constraints which are held in place radially by the bolts which fit in those holes. With that, there's really nothing else to do except modify or set the size of the mesh that we want to utilize. So in this case, we will go with a couple of, we'll make these a little bit more fine than default. Let's go ahead and mesh the component. And literally, there's nothing else to do now except run it. Again, one of the chief advantages of using dynamic simulation in this regard is that it takes all the guesswork out of it. The forces which are generated during the movement of the assembly are what we use to stress or test the component itself. Now, let's take a look here at some convergence. Before we do that, we're going to just show that you can animate the results. In this case, we're going to animate the stresses being distributed over that mount piece. And now we're going to zoom in and take a look at convergence. And what convergence allows us to do, the convergence tool in stress analysis in Inventor, allows us to validate that the results that we're getting are basically good results. So what convergence actually does is it iterates through changing it goes to finer and finer mesh densities, and then it essentially just looks to see, are the results getting better and better as the mesh gets smaller. And as you can see, they are. So we are converging on a solution, so we can basically have high confidence in these results that what we're looking at is an accurate representation of how the part is stressed. Probe tool can be used to essentially query the part for stresses at any particular point on the model, and that's pretty much it. That's an overall look at the dynamic simulation and stress analysis environment in Inventor Professional. With that, I'll pass it back over to Jorge.
Awesome. Thanks, Jay. Yeah, so, you know, as Jay mentioned, you know, we wanted to make sure we showed you some more dynamic simulation in there. I think a lot of our users here, I've seen the list here, there's some that have used it, some that have asked about it, so hopefully that gave you what you were looking for. Let's see, I'm going to look at the question and answers here now. Let's go into the question and answer. We got a question here, any way to do impact?
Yeah, you can do impact, you just can't do, I mean, it doesn't handle penetration other than contact. But yes, you could definitely do, as it pertains to linear, structural, and stress, yes, you could do an impact. It will calculate, you know, parts bouncing into each other. If I created a plate, you know, as a floor and then drop an assembly, it will do that. Where that starts getting sketchy is once results start going into nonlinear. For that, you need the simulation mechanical tool, which will do, that goes one step beyond this. Hopefully that's the answer you're looking for. But yes, you can do, I guess I would frame it and just say, if you're looking to do drop tests where things break, no, this isn't the tool, because that type of analysis it requires nonlinear solving, and this tool is basically just linear stress and strain. There's no buckling in it. It does have modal, so vibration is supported, but not fatigue, not nonlinear. I wonder if the InCAD tool, I know the InCAD tool does, so I'm not sure if you'd have to go to sim mechanical or not. You may just be able to get away with using the InCAD, the Nastran InCAD, because that does nonlinear, that does fatigue, that does buckling. I would look into whether or not InCAD supports it or not. I know that Simulation Mechanical does. I've done Simulation Mechanical drop tests before. I modeled an iPhone a couple of years ago, and we were looking at, what exactly does it take to get the screen to crack? And as anyone who owns an iPhone and has dropped it, it's not a whole hell of a lot. I mean, you can drop it from about 12 inches up on a marble floor, and it's gone. But
Yeah, to add to that, yeah, I agree. InCAD and mechanical, they both do the impact there, especially for large displacement, I think is the key point there.
yep,
And actually, there's a little more on that question. The person, Lauren, is actually asking, for example, stress on a bench when a weight drops on it from a 1 foot height, which I'm thinking that'd be more something for like simulation mechanical or NASTRAD InCAD, right?
I agree.
Especially because the tools in there kind of give you a little wizard to walk you through. So if you want more information on that, Lauren, we can definitely provide that for you. But that might be something like that. You might be looking more at something like simulation mechanical. All right. I feel that a few of the other questions that were pretty straightforward ones, there was one like, is this just embedded inside of Inventor? So I answered it by saying that it's an Inventor Professional, actually. So if you have a Product Design Suite Ultimate or Inventor Professional, this comes with it. So for those of you that have seen the stress analysis, if you have that already, the FEA inside of Inventor, then you have dynamic simulation. So anyone with Professional or Product Design Suite Ultimate, you will have access to this. All right. So just really quickly, if there's any recommended next steps I could give you, I'd say explore it. Maybe you didn't realize you do have access to dynamic simulation. There's plenty of tutorials. There are YouTube videos on this. We did record the session too, by the way, so we should have this up on our YouTube channel fairly quickly. Just go to youtube.com, of course, type in KETIV, and then we'll have a playlist on there for all our AVA sessions. If you need more, like we started mentioning here, you might need to do more than just what we saw today. This was just one example, of course. There's a lot of different examples of where you can use dynamic simulation. I've seen things from wiper blades to maybe having a gate that needs to close and wanting to see what the forces were where it's actually hitting the different components and things like that. But don't forget there's other solutions as well, simulation mechanical, NASTRAD and InCAD that will take large displacement, or if you have nonlinear materials, like rubber, plastic, and things of that nature as well. All right, so with that, we'll go ahead and wrap this up. I'd like to thank everybody, and again, if you want more updates, we're on the different social media sites. Visit our blog, our YouTube channel. I strongly encourage you. This is recorded again, and all of our past sessions as well. So thanks, everybody. Thanks again, Jay, and we hope to have everybody back soon. Next week is Process Automation with Vault.
See you guys.